All right. Thank you very much, Katinka, for the introduction. Sorry, I'm just getting set up here with the screen sharing. So now can you see my screen?
Yes.
All right. Yeah, thank you for the introduction and for giving me the opportunity of presenting some of our work here. Indeed, we've done a lot of work on blockchains, first with my team in Sydney, where I spent about 10 years, and then now since mid last year here at Berlin. And I specifically pick out the parts that I think would be most relevant for the audience of this forum. And so I focus on some data analysis from blockchain data. But because Katinka and I had a discussion, and I had, in fact, a discussion numerous times, before we go into detail of data analysis, I just wanted to highlight a few definitions when talking about blockchain, because Bitcoin did a particularly good job in using the word Bitcoin for everything. So Bitcoin is, the cryptocurrency, it's the network, it's the technology, everything is called Bitcoin. And so when we started doing research on blockchain about 5 years ago, we thought, okay, this is really confusing. And many of you may know this, the parable of the blind man and the elephant. I'll just summarize it very briefly. So assume here there are 4 blind men investigating an elephant, and they're looking at different parts of the elephant. And from what they are seeing and what they're observing, they are saying, the first one is saying, oh, the elephant is like a big snake. And another one says, no, it's like a tree stump, etc. And so blockchain is a little bit like that. Some people might say it's a database, and others say, oh no, it's actually a network, and yet others might say it's a code execution platform. And so starting off from that, we said, okay, why don't we come up with a set of definitions for disentangling this mess and tying down a few terms to a specific meaning. And so starting from distributed ledger, which is an append-only data store of transactions distributed across machines, we then define blockchain as a particular type of distributed ledger, which is structured into a linked list of blocks. And the blocks each contain an ordered set of transactions. And we use cryptographic hashes to secure the link from one block to the predecessor. I'm sure you're all familiar with variants of such a picture as here on the bottom. So this is on the conceptual level. What's a distributed ledger? What's a blockchain? As concepts, right? And then we define a blockchain system as a concrete network of specific nodes of machines that interact with each other and having a concrete data structure. So the blockchain data structure, the ledger, which is distributed across the network, and you have a network protocol in there. And a particular type of blockchain system is a public blockchain, which has a few specific characteristics like an open network. As per our definition, it needs to have the feature that each full node can completely verify new transactions and blocks, as well as an incentive mechanism to ensure the correct operation, like the block rewards and the fee structures, etc. And then finally, a blockchain platform or blockchain technology platform is essentially the software you need to run it. So if you're talking about Geth and parity and what have you for Ethereum, then that would be part of the blockchain platform or blockchain technology platform, which you can deploy separately and create your own networks, of course. And then we also have definitions for smart contracts and decentralized applications. Smart contracts, I'm sure you're all familiar with very well. We're just saying here that there are programs deployed as data and executed in transactions on the blockchain, and a few more things. But decentralized applications, we call them decentralized applications or dApps when the main functionality is implemented through smart contracts. Now, there are many other types of applications which may use the blockchain somewhere in the middle. And these we would call blockchain applications. So decentralized apps are a particular type of blockchain applications which provide the main functionality through smart contracts. And these definitions, I have them here in verbatim from our book, not because I want to read them to you. I think that would be very boring, but just because I will provide the slides later on for you. And these are essentially in there for your reference. And all the definitions I talked about are from this book that we published last year and that has been relatively well received and been taken up and downloaded many times. All right, now sort of to the core of the topic, extracting and analyzing blockchain data. So here I have essentially two, I'm working along the lines of two specific tools I want to show you. The first one is one that we have deployed quite a while ago, and it's available publicly on the internet. No need to create an account or log in or anything like that. You just open the website ethviewer.live and you can see what is currently happening on the Ethereum blockchain, right? What you see happening here in the background is, that WebEx is resource hungry. Okay, usually if I don't run WebEx in parallel, I get 500 transactions here in the transaction pool being displayed. So these are transactions that are waiting to be included in new blocks. And here the rectangles, these are the blocks. The newest block is on the left. Every second, we shift it down by like 1 pixel roughly speaking. So in the y-axis dimension, you can see how much time has passed. So between these 3 blocks here, for example, next to no time, then here was a little bit of a longer delay. And then here's that button, which is why I'm showing it to you today, which is the extended view. And the extended view is not displaying very well on the screen today. Let me just try that again. Okay, here we go. The extended view now splits the transactions in the transaction pool by gas price. Okay, so up here you see the x-axis labels for the gas price. It's a logarithmic scale. A lot happened in the past year or so down here between 1 and 10 gigaway. And now we're up to, 50 and even 100 gigaway with the current exchange rate. That is actually quite a bit of money. And what you can see, especially if you're looking at the version where you can see 500 transactions in the transaction pool, you can visually observe that the transactions on the right side of the transaction pool are being picked up more frequently than the ones on the left side. So gas prices do matter in terms of how quickly a transaction is included in the blockchain, in the Ethereum blockchain. All right, I just wanted to highlight that very quickly. might be nice for some of you, especially if you have new staff or students, to show them this visualization. We tried it out even with politicians, and they sort of understood the blockchain using this metaphor even in 2017. So it's quite useful for that as well. Now, the other thing is if you're in the position that you want to analyze data on the blockchain, especially if you have a decentralized application or a blockchain application in general, then you have the smart contracts deployed. And of course, what you include in such smart contracts is up to the developers, but then how it is being interacted with is of course up to the users. And one feature of blockchain is censorship resistance, right? So anybody can call any smart contract at any point in time on a public blockchain. And then you don't have control over how the users interact with your smart contract. And so because of that, but also in general, just because you want to understand what the users are doing, or even if there are failures that you need to understand, or you want to do auditing, or just monitoring live what is happening, how your application is being used, then extracting data from the blockchain is essentially what you need to do. And the data is in principle there. It's on the ledger, right? If you want to interact with a smart contract, you submit a transaction, the transaction invokes the smart contract, the function is executed, etc., etc. However, extracting this data that you want to then analyze and understand how your users are using the dApps, or somebody else's users are using their dApps, that can be inconvenient and slow. And in particular, it's subject to interpretation, right? So for example, the most trivial example in a public blockchain is, when do you see a transaction as committed? We might agree that 12 blocks now is a sufficient number of confirmation blocks on the Ethereum blockchain, but you go to one of the exchanges, let's say Poloniex, and they are using 54 confirmation blocks, right? Before they see the transaction as committed, before they credit the money you have transferred into your account on Poloniex into your account on their platform, and you can start trading, they wait 54 blocks. So this is the kind of interpretation that I'm talking about. Also, if you take the block timestamp and you say, okay, that's the timestamp of a transaction. Well, not really. On the public version of the Ethereum blockchain, that is the time when the miner started mining, because it's part of the block header, and therefore it's part of the hash, and therefore they don't want to change it after they start mining, right? So it's when they started mining, but this is, then the block didn't exist in the ledger. It was just locally in their main memory on their machines. So then you might say, okay, I'm using the timestamp of the next block, but then you have the 12 confirmation blocks, so you're using the 13th timestamp. And you might say, okay, that's how I want to do it. But if you have the common situation that you're using the blockchain because you want to interact with other parties, then this interpretation of when the transaction has been committed and when something has essentially happened, this interpretation should be shared among those parties. And so because of these reasons, and because also generally we found that there was no logging framework for the Ethereum blockchain, we created one. And that is what you see here. That is our approach, the Ethereum logging framework, ELF. And this was, of course, done in collaboration with my former team in Australia. So it's a highly configurable and open source tool. There was a predecessor version of it, which I'm just listing for reference, which only focused on process mining kind of aspects. And with ELF, we significantly broadened the application space. So let's say you have your blockchain and things are happening, transactions are being written, there is a certain state, there are transaction receipts, and then you want to extract data and you want to, let's say, output it in CSV format. So for that, we have an extractor, and the extractor uses a manifest. So in the manifest, you specify how the data should be extracted and written into a CSV. Now the manifest, you can of course make syntax mistakes and whatnot. It's a specific language in which that is written. So we have a validator for checking the syntax, and you can check your manifests before you try and execute them. So this is what I just talked about. Was you have some application, somebody else's application, let's say the Augur marketplace, right? Prediction marketplace, then you write a manifest on how to extract data from Augur, and you can run that manifest with the extractor and get your CSV data. We also have a few other output formats, which I'll talk about in a moment. But then there is this other arrow here, which I want to mention. So from the manifest, so assume now for a moment that you don't already have an existing application, but you're in the process of developing a new application or a new version of your existing application. Then you can first write the manifest and afterwards use a code generator which generates Solidity source code, which is logging code. So think of your favorite Java logging library. It's kind of like that, except we have to create it from the manifest because otherwise it would be tremendously wasteful, and you don't want to be wasteful with your smart contract code, especially in terms of storage space. So this is the best way we found to come up with a logging framework that is actually useful in the blockchain setting, where you need to have everything space optimized in terms of both the source code, but especially also in terms of the data which you're storing on the ledger. All right, so if you're using that path, then you get your logging code and you integrate that with your application code. You deploy your smart contracts, run them, and then they again create the data, and you can run the extractor again, and of course get the data outputted in your preferred format. Okay, so just going into a little bit more detail on some of those features. So the manifest is essentially the specification of the interpretation, right? Should we use the timestamp that's 13 blocks after the block that included your transaction? That you can specify in the manifest, and then you can share that manifest across the set of participants with whom you are collaborating or interacting over the blockchain, and then everybody has the same interpretation. Or you can use that in when you're writing your scientific papers, because you can publish the manifest with it, as an online appendix or what have you, and then say, okay, if you want to rerun our experiment, you don't have to try and guess how we interpreted the blockchain data. Here's the manifest. You just run that. You get the CSV file that looks exactly the same as the one from which we did our data analysis. And data output can be in CSV, can be comma-separated values, which is of course very easy to use in all kinds of data analysis tooling. It can be just in textual format, and it can be in XES. XES is the extendable event event structures. So this is for process mining tools, and you will see a few instances of that as well. So if you want to understand, for example, if you have kind of business applications running on the blockchain, you want to understand the business process that is happening here. And the data can be extracted as a one-off type of run of ELF, or it can be streamed. And of course, it's not streaming in the sense of, every 1 second or whatever you're publishing a new event. It's streaming where you have a new set of events being created every time there's a new block. And then you can process that using streaming tools. And last but not least, the logging code generation, as I said, creates space optimized storage of required data. So for example, if you have enums, so you have a list of possible values, for example, like colors, then you can essentially send the string red to the logging code, and that is translated into a bit array. And actually multiple bit arrays can be combined so that we're making best use of the word size in the memory of the blockchain. And so it's really quite tightly optimized. And then, of course, you don't want to deal with these bit arrays and pass them again. But you don't have to, because, of course, as I said, you can use that exact same manifest from which you created the logging code to then extract the data. And in your smart contract, you write the word red into your log message, and you get a text file that says red, for example, or a CSV file. So the translation happens on both ends. Now, a few selected use cases of ELF. So the first one was just a simple block statistics. So here you see the Ethereum, public Ethereum blocks between about 6 million for 1,000 blocks. You can see how the number of transactions increased slightly and how the reward in Ether went down. Now this is in Ether. The exchange rate might have gone up more dramatically than that, and therefore the dollar value would have gone up as well. That we, of course, cannot see from the blockchain data, because the data on exchange rates isn't on the, it's probably by now on the blockchain in terms of decentralized exchanges, but we didn't look into any one of those for this extraction. Then I already mentioned Augur as a prediction marketplace. So we can just, for example, take the Augur contract register updates and output them in a textual log format. And so this looks like an ordinary log file, which is exactly the point, right? So here we wanted to just output log files as any other application log files, Apache, HTTP server, MySQL, what have you, so that all the tooling you have for processing log files could be applied here. And yeah, I should have said for the basic block statistics, we just outputted a CSV file, and then it's very easy, of course, to visualize that using Excel or any other tool for processing that data. And then the XES format you can use for process discovery. So here we use the famous CryptoKitties example. So the CryptoKitties is a game. It was the first one to trigger a high number of transactions that really brought the Ethereum into its throughput limit. And you can apply our ELF framework on that and essentially generate this of CryptoKitties executions, contract executions, and then we can model that as a business process. But actually, we didn't model it. we use tools to automatically create the business process model from this log data, and that is process discovery, the technique that we use to get from XES to the nice BPMN process model you see here. Process discovery, which is one of the 3 flavors of process mining. And then here is one last use case, again from the Augur markets, where we used XES export and then process discovery again, a different modeling notation here. And here you see 3 parts of the process. Unfortunately, I did not realize that the graph was in German, so forgive me for that. But here is the first part where a market is being created. Here is the possible dispute about a market, and here is market finalization. Right, so you basically go from this. This is the same activity, and this is the same activity as here. So you can puzzle them together in your head. Now, here's the interesting part. The dispute round. You have 284 cases going into the dispute round, and then you have 904 executions of this first activity, and you have 183 cases coming out of the dispute round. So somewhere between entering the dispute round and exiting the dispute round, 100 cases disappeared. That basically means, and in some cases, obviously, we must go through the loop here. So the loop has about 600 instances. That basically means some people just keep on disputing particular cases, and the dispute resolution process doesn't actually resolve it. Now, I think from this example, it's fairly obvious that if you are, in fact, the product owner of Augur, this would be useful information. How are people using the dispute round? Maybe we have to change something in the next version of Augur in order to not lose so many cases here in the dispute rounds, where people probably just give up because they say, oh, if I just waste more transaction fees on keeping the dispute going, the others will just keep on disputing it and I'll never get anything out of it. Probably that is what we suspect as the reason behind it. All right. And then very briefly, I just want to also highlight our work on cost modeling and estimation. So this is probably relevant for some of you, probably not so relevant. So I'll just go over it reasonably quickly. The general version of the paper, we started with the words, the cost of distrust. So that's the start of the title. The cost of distrust. How much more does it cost you to use a public Ethereum blockchain instead of just Amazon Web Services Cloud in the specific case of the evaluation? And for that, we created cost models for Ethereum, cost model for Amazon Web Services, and I won't bore you with all the details of it, but we did apply it to a business process instance, right? So you don't need cost estimation for individual transactions, okay? But you may want to understand if you implement a complex business application on top of blockchain, where you implement a process like the one shown here, which has 5 different parties that are interacting and that are sending messages, sending transactions into the blockchain. You do want to understand how much does it cost me on the level of the whole application to run this process in the cloud. And this is, of course, something completely different from understanding the cost of a single transaction. Single transactions are a very important part of the cost model, but there are other factors. But what we want to do is estimate the cost on the level of the application. And for that, I'm just going to briefly explain some aspects of the cost model of the blockchain side. So if you take the process model that I've just shown and you translate the first two interactions into a sequence diagram, this is roughly what it looks like. The bulk buyer is making an API call for ordering goods, is calling its own interaction component, which we called trigger in our first work. So this is a regular, RESTful API call. The trigger component takes that, translates that into a blockchain transaction, calls the smart contract with it. The smart contract takes the conformance and writes an effect, which is picked up by the trigger of the manufacturer. Manufacturer's trigger sends a RESTful API call to their, ERP system or what have you. And so the smart contract, we have exactly one. But for the interface components, the triggers, we have one per party that is in the business process. And then, of course, we have, your ERP system running locally for each of the parties. And we don't need to consider that because the cost for that is the same for cloud and blockchain. All right. And just to highlight one aspect, just to give you a feel for what the cost estimation framework looks like. A fair number of formulas. So this is for creating a smart contract. So you have the data with the bytecode of the compiled contract, and that you multiply by the gas price per byte. And then you have a few other things. So creating a contract costs you the cost for the transaction plus the cost for creating a new address for the new smart contract, plus the cost for the payload data, plus function definition cost for the opcodes which are executed when the deployment is happening, right? And so if you do that through another contract, then it's a slightly different cost. And so for all the different components of where cost is incurred, we have formulas like that. And then similarly for Amazon Web Services, we use their simple workflow tool, simple workflow, SWF. And then we ran it. And so we ran 32 process instances on the blockchain and at an exchange rate of $420 per Ether and a gas price of 2 gigawatt for each transaction. Each instance cost us $1.34 US. Now the cost for Amazon Web Services was a little bit lower, so we paid less than $1 for 1,000 process instances. And so, you can have a look at the papers and get all the details also over the history. And of course, the exchange rate is something where we need to be careful. Just two aspects that I wanted to highlight. The blockchain stores the results in perpetuity. So for the lifetime of the blockchain, you'll never have to pay again. For Amazon Web Services or any other cloud provider, you typically pay by the month or by the day. And in order to reach break even, right? How long do I have to keep the data on SWF to reach break even for it to be the same cost? That would be 668 years, all right, with the exchange rates that we saw previously. Okay, so maybe you're not that interested in keeping the data stored for quite that long. However, there's one more aspect which I want to highlight, which is this part here. Public blockchain supports payment and escrow out of the box free of charge, right? You're already paying for the escrow whether you use it or not. So you could transfer money into the smart contract or any other type of asset, and then only when certain conditions are reached, that money or the assets are transferred to somebody else. And that comes for free on the blockchain. If you want to use commercial escrow providers, they charge between 0.5 and 3.25% of the value of the transactions. All right. So you don't have to go very far. If you have a value that you store in escrow of somewhere between, $10 and $100, you're already breaking even. So if the value you store in escrow is higher than that, it's cheaper using the blockchain than using a cloud provider plus a commercial escrow provider. All right, with that, I want to end my talk and look forward to the discussion with you.
Thank you very much. Are there any questions? I think you can just turn on your microphone and ask your questions.
Someone turned on their microphone, but I don't hear a question.
Can you hear me?
Yeah, now we can.
Sorry, hold on. It's a bit scary to just start talking, so I also raised my hand, but
I didn't see it. Sorry.
Okay, no problem. Thank you very much for the talk, Ingo. In particular, the last bit actually was a bit of an eye-opener, in that you can just sort of think about blockchain as a competitor of other ways of computing, in particular also cloud computing. That's very interesting. I had actually two questions, maybe starting with the last bit on this cost. Where do you see the research going, or where do you think this should result in tools that people could use? How do you see that develop?
Sure. I mean, you could you could extend, probably is the way to go. Extend tools with simulation features, with cost estimation features. Those could be, of course, process modeling tools, but they could also be, software architectural modeling tools. Maybe also for data modeling, because actually, I don't know if you looked at the yellow paper of Ethereum in detail and where the cost is being created, but let's say you're comparing two variables that cost you about 10 gas, but then storing a value in a not previously initialized variable costs you like 20,000 gas, right? So 10 versus 20,000. And so for data modeling, I think this would be tremendously useful. I've also done quite a bit of work on model-driven engineering for blockchain applications, which I didn't talk about much today. But we haven't done the data modeling part in so much detail. I think there are other approaches where they do that. So I've seen something where they create like an ER model, and then they say, this field goes onto the blockchain, and this field we just hash and put the hash on the blockchain. And for this other field, it just stays locally in our database. And of course, something like that would really benefit from cost estimation. I should also say with this work, it was quite funny because when I was with CSIRO in Australia, we did quite a few industry projects and government projects as well. And usually we would reach the point where they would say, okay, now you created this beautiful architecture for us, but how much will it cost us? Or how will the throughput, what will be the maximum throughput? And if you know Ethereum well, then you know that throughput and gas consumption is directly linked, because the block size is specified not in the number of megabytes, but in the maximum amount of gas. And so the gas you consume is also where the cost is coming from, if you multiply that with the gas price. But that also gives you the throughput then. Yeah. And quite often these customers would then say, how much will it cost or what will be the throughput? And we basically just pulled out our paper, dusted it off and said, here's the cost model. Shall we go and execute that for you? That worked really very nicely.
So in your experience, Ingo, do you see companies start to make this trade-off about should we put it on the cloud or should we put it in blockchain, or is blockchain still somewhat more of an obscure technology that companies wouldn't necessarily trust? How do you see that?
So I've just seen some public documents of SAP where they talked about putting business documents on the blockchain, but not the whole document, but rather what they do is actually pretty clever, because they imagine a business document, let's say a customer, a sales order, right? So you have data fields for, who's the customer, you have data fields for the line items, for the prices, etc., etc. And then you can imagine putting that into, let's say, an XML tree, into an XML data structure. So it forms a tree. Now, over that tree, you can compute a Merkle hash. So you can interpret that like a Merkle tree, compute all the hashes, and then you get your root hash for the whole Merkle tree. And that's what in the SAP case they want to put on the blockchain first and foremost. Of course, that means you cannot do any computation on the concrete data in your smart contracts. So I think if we think of combining aspects here, like having parts of the Merkle tree which represents your data structure, where you don't want to share the actual data fields, so you just put the root of the subtree. And for data where you want to do computation in your smart contracts, then you put the actual data. And I think that's entirely doable, and you get some nice guarantees in terms of overall integrity and computation on the smart contract, etc.
Very interesting. Thank you very much.
Thank you.
Hey, this is Dominic. I have one question about the Ethereum logging framework. I know that in practice, a lot of projects, especially like in this new DeFi space, they use this thing called the graph. And I was wondering how maybe the ELF compares with that. Like, can I use that basically to build like custom queries to kind of get to know what's going on in my smart contracts, or like how would it use in practice?
So I'm not familiar with the reference you just gave. Maybe you could put a link in the chat, and I can have a look later on. Yeah. But let me just go back quite a few slides to the architecture here, or architecture overview, I should say. Right, so you have your smart contracts on the blockchain that emit data, and in some local client, this data is stored, and from there you can extract it using the manifest. Right? So you could basically stream the data using any of those formats. Maybe you should add a JSON output format as well. You could stream it and then put it into a local database as well. And then you could query the local database. But yeah, you can also, imagine your complex event processing tooling over here, which is being forwarded the data, or your logging framework. So, for example, ELF could simply write into a local text file like any application log, and then you could use tools like Logstash that pick up any changes and transfer the data from those changes into like Elasticsearch or whatever you want to do with it.
Right. I could also probably upload it to IPFS or something like that, and then do some like custom queries over it. And okay, so the framework is really about exporting this data from Ethereum, and then you have to handle like that on a database level to do the querying and the
Yeah, exactly. Yeah. So we're not dealing with what you do afterwards once you extracted the data as part of this framework, but indeed, so we have a group of students. Well, it's the first week of the semester. We don't have the group yet, but next week a project will start with I think 5 or 6 master students who will also contribute to extending the framework into various directions. And then I want to have a master thesis or two about, connecting ELF with other tooling. For example, from the process mining space, then you can do a live comparison with between a process model and the data that is happening, or things like that. Outcome predictions, predictive monitoring, things like that. So really quite versatile in that sense, but yeah, we haven't looked at structured ways of using the data that we extract.
Yeah, that makes sense. Yeah, I think the graph is sort of maybe on a different aspect of this, where it provides like this GraphQL interface where you can query basically across your smart contract. And maybe, I don't know, ELF could be integrated as like a data source to that. But I posted the link there, and thanks very much. Very helpful.
Yeah, thank you for the reference. I'll have a look at it.
Any more questions? No, doesn't look like it.
All right, thank you very much, everyone. I'll stick around until the break. Afterwards, I have to deal with more first week of the semester kind of aspects. And yeah, thank you for having me.
Thank you very much for joining, and thanks very much for your talk. And discussion will follow, I'm sure. So next now.
Hi, Katinka. Yeah, sorry to interrupt you. So this is Danilo from Milan, and actually I want to welcome you to the workshop. Sorry, I'm jumping to each workshop that are running in parallel today. So I take the opportunity of break to welcome to the workshop and to thank Katinka and actually William for organizing this interesting workshop. So I think, I mean, you have a very interesting program, so enjoy the workshop, and yeah, see you later. Okay. Sorry for the interruption.
Thank you. Thank you very much. So now we move to the next talk, which is predicting confirmation times of Bitcoin